Hello, this is Lecture 2 of ComSci 141, Deterministic Finite Automata. Previously, we introduced automata and discussed the central concepts, which are alphabets, strings, and languages. In the Finite Automata outline, we are currently on the first topic of Deterministic Finite Automata. In today's video, we will discuss finite automata, deterministic finite automata and its notations, and how the extended transition function works. Previously, we ended with the membership problem. We asked if L is a language over sigma, given that the string W is in sigma star, decide whether or not the string W is it part of language L or not. So is string W part of language L? Or does language L accept string W as part of the set? Okay, so this is language acceptance. And our finite automata is a very simple computing model which acts as a language acceptor. So it takes as an input a string, and the output is whether yes or no. And that means that either the string is accepted as part of the language or not. So the finite automata is a very simple model. It has very limited memory capabilities. So it is not a general model of computation, and it only works for some languages, specifically regular languages. So what is the finite automata? It is a finite state machine. So it has some states, and it has a starting state, accepting states, and other states. It also has transitions. So from one state, it can transition to another state given an input. And there's also a control or a pointer that transitions from state to state in response to external inputs. And that's it. So the finite automata only remembers what state the control currently is. Okay, so that's the only thing it remembers. Where is the control currently in? Okay, what state is it currently in? So it's a good model for computers with extremely limited amount of memory, because it only remembers one thing, and that is where is the control. An example of such system with limited memory is a turnstile. So you've probably seen this in the movie house or in train stations, right? So a turnstile's finite automaton would look something like this. At the start, the turnstile is closed, right? So at the closed state, no matter how hard you push it, it will remain closed. It will only open once you insert a coin, right? So when you insert a coin, it transitions to the open state. Now, once it's open, no matter how many coins you insert, it will remain open. And it will only close again once you pass through the turnstile and you push the lever, right? And once you push it, then it becomes closed again. So this is the simple finite automaton for the turnstile. Now, for finite automata, we have two types. We have the deterministic and non-deterministic. For deterministic finite automata, or DFA, given one input, one state transitions to exactly one state. So it's determined where you will go, okay? Because you'll only go to one state. However, in non-deterministic finite automata, or NFA, given one input, one state can transition to more than one state. So we will see this in the later lectures when we discuss non-deterministic finite automata. But for now, we'll focus on the deterministic finite automata. So for each input symbol in the DFA, there is only one state to which the automaton can transition from its current state. Okay? So let's see an example. let's say we have the language wherein it's a set of binary strings that ends in 1. So we could write this in set former notation. So it's x1, wherein x is any string of zeros and ones. So as long as the string ends in 1, it's part of the language. So how many states do we need in our DFA for this language? In fact, we only need 2 states. So this is the DFA for the language of binary strings that end in 1. So at the start, we have an empty string, right? So we don't see anything yet. So of course, that does not end in 1 yet. So that's our starting state. Doesn't end in 1. Now, if you see zeros, that still doesn't end in 1, so it will stay in this state. It will only change states when it sees 1. So when it sees a 1 input, then currently it ends in 1. So it will change to this state, ends in 1. And if you see 1 in this state, it will still end in 1. But if you see 0 in this state, it will go back to does not end in 1. Because, well, it now ends in 0 because the last symbol that you saw was 0. Okay? So if you end up here in ends in 1, then it's accepted. So you see the double circle here. That means that it's an accepting state. Okay? So this is the simple example of a DFA for binary strings that ends in 1. And if we don't want the verbose state name, we could just label this with a variable name. So state A or state B. So state A represents the state of not ending in 1, and state B represents the state of ending in 1. Okay, so you can write your DFAs like this with just letters as state names. Okay, so what we saw was an example of a transition diagram, and it's a graph representation of the DFA. So you have your states as the nodes of the graph. Your transitions are shown as directed and labeled edges. So going back here, this is a directed edge. So this is from A to B, right? So that is the transition from A to B. And there's also a label, which is 1. What this means is that this transition happens if you see an input 1. Okay? So the transitions are directed and labeled edges. You also label the start state with an arrow labeled start, as we saw earlier. And the accepting states are nodes with double circle. So going back to our example, so we have our start state here labeled by the arrow with the start, and the accepting state is state B because it has a double circle. Okay, so that is the transition diagram. Now, some of the common mistakes in creating your transition diagram is, first, you don't label the edge. So you must label the edge for us to know what input does that transition happen. Okay, so you label the edge, and then you also don't you might also forget to write the start arrow. So don't forget that one, so that we know where to start, which state to start. And the other one is accepting states are not in double circle. Okay, so always remember that if it's an accepting state, you must wrap it in double circles because that would be the hashtag goals, right? Okay, so that's it. Now, transition diagram is only one of the DFA notations, or how you can write the DFA. So there's actually three ways that you can write the DFA. So there's the 5-tuple notation, the transition diagram, which we have just seen, and the other one is the transition table. So let's take a look at the 5-tuple notation, which is the most formal way of writing the DFA. So the 5-tuple notation is for the DFA consists of, well, 5 things, right? You have Q, sigma, delta, Q sub 0, and F. So what are these things? Q is just the finite set of states of the DFA. Okay, so set of states. Sigma is the finite set of input symbols, or like the alphabet of the DFA. Okay, delta is the transition function. So it will tell us what states transition to which state on which input. So it maps states and input symbols to another state. Okay, so we'll see this in the next slide in detail. And then Q sub 0 is the initial state or the start state, and Q sub 0 must be part of the set of states, Q. And then finally, we have F, which is the set of final or accepting states, and F must be a subset of Q as well. Okay, so your accepting states could be 1 or more, or even 0, no, if you don't have any accepting states. So, but usually there should be one, because if we use DFA as a language acceptor, there should be at least one accepting state for us to be able to accept some strings in the language. Otherwise, it would be an empty language, right? Okay, so that's it. So take note, F is a set, so it could be one or more. So let's take a look at the transition function in detail. So the transition function delta looks like this. Delta QA is equal to P, wherein Q and P are states and A is an input symbol. And what this means is that when the DFA is in state Q and it receives input symbol A, it will transition to state P. Okay? So the graphical representation of this is a directed edge labeled A from state Q to P. So it will look something like this. So if there's a state Q here and there's a state P here, this transition will be a directed edge from Q to P labeled A. Okay, so this would be the graphical representation of the transition. Okay, so let's see an example of the transition diagram, and then let's write its 5-tuple notation. So for Q, which is the set of states, we have A and B because we only have two states here in this DFA. For sigma, we have 0 and 1 because the input symbols that we have are 0 and 1. Next, we have 4 entries in our transition function. So let's start with delta of A0. That would be A because A on 0 still goes to A. A on 1 goes to B because of this transition. B on 0 goes to A. So B on 0 is directed to A. And B on 1 goes to B. Our Q sub 0 or our start state is A. And our final or accepting states is just the set containing B, since we only have one accepting state. Okay, so that is how you write your 5-tuple notation. Okay, let's take a look at the other notation for DFA, which is the transition table. The transition table is a tabular version of the transition function delta. So it contains all the DFA information in this one table. So what we'll do is we'll write all the states in the rows, the table rows. And then the input symbols will be our table columns. And then the start state will be marked with an arrow, and the accepting state would be marked with asterisks. So if there are multiple accepting states, there would be multiple asterisks. And then the rest of the table will fill in with the transition function. Okay? So as an example, this was the DFA that we had earlier. So in our transition table, our states are here as the rows, so A and B, and then the input symbols are 0 and 1 in the columns. So our start state is labeled with the arrow, so it's A, and our accepting state is labeled with the asterisk, which is B. And then for the transition, A0 goes to A, A1 goes to B, B0 goes to A, and B1 goes to B. So everything is encoded in this one table. So that is the transition table. Okay. So now that we have seen how to write our DFA in 3 different ways, so we have the transition diagram, transition table, and the 5 tuple notation, how do we actually design a DFA for a given language? So these are the steps in designing your DFA. Number 1, you start with the start state. And then, for every input symbol in this in Sigma, you need to ask, where do you go? Should you stay in the current state or should you transition to another state? Okay, so that is what we need to ask. If the state does not exist yet, then you create it. Okay, you add a new state if it does not exist, and later on, you identify which states are the accepting states. Okay, so you wrap them in double circles. And it's also helpful to write state descriptions so that you are guided as to what state A, state B, what state C is. Okay, so write a description. So for example, A does not end in 1, B ends in 1, something like that. Okay. Now, take note, however, that the DFA needs to have a unique transition for every state and input symbol. So the transition table must be filled up. So there should be no blanks in there. So for example, for an input for a state and input symbol, for each state and input symbol, there should be an entry in the transition table or transition function. Okay? So if no transition from state Q on input A exists, we need to add a dead state or a sink. Okay? So this is where all the non-existent transitions will be directed into. Okay? Because our DFA needs to have a unique transition for each state and symbol. So if wala siya, dugangan mo lang sang extra, you need to add an extra state wherein you direct all non-existent transitions there. So we call that the dead state. Okay? So let's see some more examples of designing DFAs. So we'll have 3 examples here. Set of binary strings with 1, 0 as substring, set of binary strings with no 1, 1 as substring, and set of binary strings with even number of zeros and ones. So both even. Okay, so let's take a look at each one. So the first is the set of binary strings with 1, 0 as substring. So in this DFA, we have 3 states. So at the start, we have start state is A, and in A, this is the state where we haven't seen 1 yet. Okay, so why are we interested in seeing 1? So we want to see if the string has 1, 0 as substring. So we want to see 1, 0, right? And once we see 1, 0, whatever comes after that, it doesn't really matter, right? As long as we have seen 1, 0, then it's already accepted because it's already a substring, right? So 1, 0 as a substring. So we are interested in seeing 1, 0, but we have to start with seeing 1 first. So as long as you haven't seen 1 yet, you'll stay in A. So if you see 0, still in A. So you still haven't seen 1 yet. But if you see 1, you transition to state B. And this is the state where you have seen 1 already. So you saw 1, and if you see another 1, you stay in B. If you see a 0, however, then you have seen 1, 0. Okay, so you will transition to state C since you have seen the 1, 0 substring, and whatever comes after that, so whether you add zeros or ones, it doesn't really matter since you have already seen the 1, 0 substring. So this is already the accepting state C. Okay, hopefully that makes sense. And the corresponding transition table for the DFA would be this one. Okay, so yeah, it's just the same as the transition diagram. So let's take a look at our next example, which is binary strings with no 1, 1. So our goal is not to see 1, 1 as a substring. Okay, so at the start, if we haven't seen anything yet, so meaning empty string pa lang siya, then we could already accept that one, right? Because that that state hasn't seen 1, 1 yet. So that is already an accepting state. So if you see 0, that's still no 1, 1, and it doesn't end in 1. So we have a distinction between the two states, A and B, because the two states does not end in 1, 1. Or, sorry, does not have 1, 1. But state A hasn't seen 1, 1, and it doesn't end in 1. So as long as it's 0, all zeros here, you stay in state A, and you haven't seen 1, 1 yet. But if you see a 1, you go to state B, because that could start triggering seeing 1, 1, right? That would be the start of seeing 1, 1. But it's still an accepting state because you've only seen 1 or isa ka 1 so far. Okay? So it's still accepted because it's only 1, 1 for now. But if you see a 0, it will go back here, right? But once you've seen another 1 from state B, so you've already seen a 1 earlier, and then if you see another 1, then you have seen 1, 1. And in state C, there is no way out because you have seen 1, 1 already. So that cannot be accepted anymore, no matter what comes after that. Okay? So in this case, what has been seen cannot be unseen. Okay? Does that make sense? So this is the corresponding transition table for that transition diagram earlier. So yeah. And for the last example, let's see the DFA for binary strings with even zeros and even ones. Okay, so we have 4 states here. State A, which is our accepting state, will have the even zeros and even number of ones. So at the start, well, we haven't seen anything yet, so there are even zeros and even ones because both counts are 0. So that is an accepting state. Now, if we see a 1, we will transition to state B because now we have an odd number of ones but still an even number of zeros because we haven't seen zeros yet. We've only seen ones. So from A, on a 1, we go to B because we'll have an odd number of ones. But from A, if we see a 0, we'll transition to state D. And that is the state of having an odd number of zeros and an even number of ones. So here, you haven't seen 1 yet, and then you saw a 0, so there will be an odd number of zeros now, and then even number of ones still. Now from B, if you see another 1, then maging from odd, back to even siya, right? So um, if you see 1, 1, that would be 2 ones, so it will go back to A, or even number of ones. Same with sa D. If you have an even number of zeros and then you see another 0, it will go back to A because then you'll have an even number of zeros again. Okay? So that takes care of A to B and A to D. Now, how about this part? So from B, if you have a you have an even 0 and odd 1. Now if you see a 0 from B, then you will have an odd number of zeros and odd number of ones. So from even here, maging odd na siya because you added another 0. And then if you see a 0 from C, then it will go back to being even, right? And then from D, if you have an odd number of zeros and even number of ones, if you see another 1 from even, it will become odd and it will transition to state C. So odd zeros, odd ones. Okay, so this is the DFA for binary strings with even zeros and even ones. Okay, so you can study this in more detail on your own time. So you can pause the video and really see what's happening. But you can see that it's kind of symmetric, right? So if you go to if it transitions on 1 to another state, it becomes odd. But if it goes back with another 1, it goes back to the original state and becomes even again. So here, same with zeros and same with ones here. Okay, And as usual, this is the equivalent transition table for the transition diagram. Now, in this example, what we are doing is the DFA counts the number of zeros and ones modulo 2. So it doesn't really count the exact number of zeros and ones. It only counts it modulo 2, so whether even or odd. Okay, so only remembers if the number of zeros and number of ones is odd or even. Okay, so take note of that. Now, finally, we said that the DFA acts as a language acceptor, right? So the DFA decides whether or not to accept a sequence of input symbols or the string, right? So language deciders or language acceptor. So given a string, is it part of the language or not? So the language of the DFA is actually the set of strings that it accepts. And we usually denote that with L of A. So the language of DFA named A. Okay. Now, how does the DFA accept the string as part of the language? So these are the steps for acceptance. First, you start in the start state, q sub 0. And then we repeatedly consult the transition function delta for the current state and the next symbol in the string. So currently where we are, and then what is the next symbol in the string. So we'll consult where to transition, what state should we go to next, basically. And then we'll follow the transition until the end of the string is reached. So current state, and then get the next input symbol, go to the transition state, and then we'll have that current state again. So repeat that until we have processed all of the input symbols. Now, if the last state that you reach is part of the final states, then the input is accepted. Otherwise, it's rejected. So it's accepted only if you reach the final state, basically. Okay, so it's simple as that. Acceptance. So let's see some examples from our earlier DFA. So given this DFA, let's test the input 1, 0, 1. So we'll start at A, 1 goes to B, 0 goes to A, 1 goes to B. So we ended up in a final state, so 1, 0, 1 is accepted. How about the next one? 1, 0, 1, 0. So 1, 0, 1, 0. It ends up in A. So it's not accepted because A is not a final state. How about 1, 1, 0? So 1, 1, 0 also ends up in A. So it's also not accepted. How about the last one? 0, 0, 1. So 0, 0, 0 still stays in A. And then the final 1 transition goes to B. So it's accepted. If you recall, this is the set of binary strings that ends in 1. So you'll notice that only 101 and 001 were accepted because those are the strings that ends in 1, right? So let's see one more example. For this DFA, let's test 111. So A goes to B on 1, stays on B on 1, stays on B on 1. So 111 ends up in B, so it's not accepted. How about 001? So we have 001 also ends up in B. It's also not accepted. How about the next one? 0100. So it ends up in C. So this one is accepted. And the last one, starting in A, we have 11010. So it ends up in C. So this is also accepted. And if you remember, this is the DFA for binary strings with 1, 0 as a substring. So you'll notice that only these two were accepted because they have the 1, 0 as substring. Okay, let's see one more. Okay, so at the start, if we have epsilon or the empty string, so we don't have anything to process, so we're still at the start state, so that is accepted. So epsilon is part of this language, right? It's accepted. How about 000? So 000 still is in A, so that is also accepted. How about 1, 0, 1? So we have 1, 0, 1 ends up in B, which is also an accepting state. So this one is also accepted. How about this one? 1, 1, 0, 0. So it ends up in C, so it's not accepted. And the last one, 0, 0, 1, 1, 0, 1. So we have 0, 0, 1, 1, 0, 1. So it ended up in C, so that's also not accepted. And if you remember, this is the binary strings with no 1, 1. So the last two examples, which has 1, 1 as substring, were not accepted. But things like the empty string, well, the empty string doesn't have anything, so of course it doesn't have 1, 1. And the others like 0, 0, 0 and 1, 0, 1, which doesn't have 1, 1 as substring, were accepted. Okay, so that is how you accept a string as part of the DFA's language. So you just start at the start state, follow the transitions by processing each input symbol, and if you ended up in one of the final states, then you accept it. Otherwise, it's rejected. Okay? And then lastly, we have the example for even zeros and even ones. So if it's empty, then of course it's already accepted since there are no zeros and ones. So that's even zeros and ones as well. For 0, 0, 0, that would be 0, 0, 0, 0. So it still ends up in A. For the next one, 1, 0, 1, 1. So it ends up in C because it has an odd number of ones and odd number of zeros, right? So that one. Next, 1, 0, 0, 1. So it ended up back in A. So this one is accepted because it has two ones and two zeros. So that's even zeros and ones. Finally, we have 0, 1, 1, 0. So that also ends up in A. So that is also accepted because it has even number of zeros and ones. Okay, so hopefully that's clear. Okay, finally, we will discuss the extended transition function. And recall that the transition function, the normal transition function delta, only maps a state Q and an input symbol A to another state P. Now the extended transition function, which is called delta hat, so there is the extra hat here. So the extended transition function delta hat maps your state Q and a string W to a state P. So the only difference is that for transition function, you take in an input symbol, but for the extended transition function, you get a string W. And this string could be of length greater than or equal to 0, so it could also be empty, right? And your output is still state P. So what does this do? The extended transition function tells us what state the DFA ends up with following the input string W. So basically, if you process the whole string one at a time, what state does it end up in? So it extends the delta from state symbol to state string, as I mentioned. So let's see some examples. What is the delta hat of starting from A given epsilon? Given that we have the DFA for binary strings with even zeros and even ones. So since we don't have anything to process, it will stay in A, right? So it's still A. How about A given string 1? So A on 1, it will go to B, right? How about A on 1, 1? A on 1, 1 will go from B and then back to A, so that's still A. How about 1, 1, 0? So 1, 1, 0, that will be D. Okay? B, 1, 1, 0. So starting from B, 1, 1, 0, it goes to C. And then from C, 1, 0, 1, 0. So C, 1, 0, 1, 0 still remains in C. So that is how the extended transition function works. So you just extend the transition function from symbol to string, and then you follow all input symbols. Formally, the definition of extended transition function is like this. So if you have the state Q, and then you're processing a string WA, so that means that the prefix of the string is W and the last symbol is A, you could actually get this by getting the delta of the state wherein delta hat QW, or the prefix, ends up in, and then get the pair with A as the input symbol. Okay, so this one will become a state. What state does delta hat QW end up in? And that state will be plugged in the transition function together with A, which is the last symbol. Okay, so string is W is a string, A is a symbol, and WA is a string prefixed by W and ends in A, as I mentioned earlier. So let's see examples of that one. So we have delta hat of A given E. So since there really isn't any prefix here, since E is empty, so it's still A, right? So it will remain in A. For for um, for A1, note that we could write 1 as epsilon 1, right? That is still 1 here. So we could write that as um, delta of delta hat AE and 1. So we know that delta hat AE here is A from the previous item. So we could plug A here and we can just have delta of A1, which is B according to our transition function. Okay? Now next, 1 1. 1 1 could be written as the prefix 1, right? This is the prefix, and then the last symbol is 1 as well. So we could rewrite this as delta of delta hat A1, because this is A and then the prefix is 1 here. And we know that delta hat A1 from here is B, right? So we have B here, and then the last symbol 1 is here. So we have delta B1 is A according to our transition function. And lastly, 110 could be written as 110, wherein 11 is your prefix and 0 is your last symbol. So we could rewrite this as delta of delta hat A11, which is the prefix, and we know that from the previous item to be A. So that's A here. And then we pair that with the last symbol, which is 0. So from A to 0, that would be going to D. Okay? So that is the formal definition of our extended transition function. So with that, we are now ready to define our language, the language of our DFA. So the language of DFA is the set of strings W such that the delta hat or extended transition function starting from Q sub 0 and taking that string ends up in one of the final states. Okay? So again, the language of automaton A is the set of strings W that takes the starting state Q sub 0 to one of the accepting states F using the extended transition function. So once we process the string starting from start state, if it ends up in one of the final states, then it is accepted by the language of the DFA. Or yeah, it's part of the language of the DFA. Okay? And we say that if the language L is L of A for some DFA A, then we say that L is a regular language. Or another way of saying it is that if the language is if the language L is a language of some DFA, then we say that it's a regular language. Okay, and we'll learn more about regular languages in the next video. So that would be our next topic. Okay, so that's it for now. So let's review. We discussed deterministic finite automata, which are very basic finite state machines. So it has states, transitions, and a control which transfers from one state to another given input symbol. Yeah, so it transitions on an input symbol. And the deterministic version is that for one state, we know exactly which state it transitions to on an input symbol. We also discussed the three notations for DFAs, so like the 5-tuple notation. So you have Q, this set of states, sigma, the set of input symbols, delta, which is the transition function, Q sub 0, which is the start state, and F, which is the set of final states. We also discussed how to write the transition diagram with the states and transitions and the start state and the accepting states, how to label them, and the transition table as well, which is like the um, you get all of the information in one table. We also discussed how to design DFA. So you start with the start state, and then you go from there. Should you stay or should you create another state? And then if there are non-existent um, transitions, you create a dead state wherein you put all of the non-existent transitions there. Yeah, and it also helps to label or give state descriptions so you don't get lost. And then we also discussed the difference between the transition function and extended transition function. Okay, so that's it for today. For our next topic, we will have regular languages and regular expressions, and we will also prove the set equivalence of the language by the DFA and regular language in, let's say, set former notation. And yeah, that's it for today, and I will see you next time.